How does NumPy's contiguous storage make arrays memory efficient? Imagine trying to pack a suitcase with clothes. If everything is neatly folded and stacked, you can fit more in. If clothes are crumpled and scattered, you waste space. That's similar to how NumPy stores data in memory. When you create an array in NumPy, it keeps all the elements in one tight, continuous block of memory. This is called contiguous storage. It's like packing all your clothes in one neat pile instead of spread out in different drawers. NumPy arrays hold only one type of data, like all integers or all floating point numbers. This uniformity means each element takes up the same amount of space, usually a fixed number of bytes. Because of this, NumPy can store the entire array as one single chunk of memory. In contrast, Python lists can hold different types of data, which means extra memory is needed for pointers and type information. This makes lists bigger and less efficient. Storing data contiguously also reduces the overhead of storing pointers or references to separate objects. Instead of keeping track of where each piece of data is, NumPy just keeps everything in one place. This saves memory because there's no need for extra information to locate each element. Another benefit is cache efficiency. Your computer's processor loads data in chunks called cache lines. When data is stored next to each other, the processor can load multiple elements at once. This means faster access and quicker computations because the CPU spends less time waiting for data from slower memory. Contiguous storage also makes vectorized operations possible. These are operations that work on entire arrays at once, like adding two arrays together. Because data is in order, these operations can process elements sequentially, which is much faster than handling each element separately. Many optimized libraries and hardware accelerators expect data in contiguous blocks. NumPy arrays fit right into this system. They can be passed directly to these libraries without copying data, speeding up calculations even more. In practical terms, when you create a large array of numbers, NumPy stores it in a dense, continuous block. This means it uses less memory compared to a Python list with the same data. For example, a list of 1 million numbers might take up twice as much space as a NumPy array of the same size. This efficiency helps when working with big data sets or performing complex calculations. So, in simple words, NumPy's contiguous storage packs data tightly in memory, reduces waste, speeds up access, and makes numerical operations faster. It's like having a well-organized closet that makes everything easy to find and use quickly. This is why NumPy arrays are so popular for data analysis and scientific computing.